our distinguished guest, Dr. Ashish Kumar Meena, the head of the Department of Physics and Electronics, Professor Manoj B., respected faculty members, and dear students. Everything is theoretically impossible until it is done by Robert A. Heinlein. Guided by this spirit of exploration and discovery, it is my privilege to introduce the Raman Lecture Series, an academic initiative of the Physics Association. The Raman Lecture Series is envisioned as a platform that brings together students, faculty, and distinguished researchers to exchange ideas, explore emerging frontiers in physics, and cultivate a deeper appreciation for scientific inquiry. We hope that this series will inspire curiosity, promote collaborative learning, and encourage the pursuit of excellence in research and innovation. On behalf of the association, I extend a warm welcome to all of you to the first lecture of this distinguished series. The series is named in honor of Sir C.V. Raman, India's first Nobel laureate in science. His pioneering discovery of the Raman effect transformed our understanding of light and matter. His unwavering curiosity, commitment to scientific excellence, and passion for discovery continue to inspire generations of physicists. Through the Raman Lecture Series, we hope to carry forward that spirit of inquiry and innovation. We are truly honored to begin this journey with our first distinguished speaker, Dr. Ashish Kumar Meena, Assistant Professor at the Indian Institute of Science, Bangalore. Dr. Meena's research focuses on astrophysics and cosmology, with particular emphasis on gravitational lensing of gravitational waves, supernova, fast radio burst, cosmological microlensing and cluster lenses, and its wide-ranging applications. On behalf of the Department of Physics, I extend a warm and heartfelt welcome to you, Dr. Meena. Thank you for taking the time to be with us today and for sharing your knowledge and insights. Without further delay, I invite Dr. Ashish Kumar Meena to deliver the first talk of the Raman Lecture Series. Thank you, and over to you, sir.
Hello, can you hear me in the back? Is it okay? you hear me? Okay, that's good. First of all, thank you very much for inviting me here. It's been a pleasure. And this is the first time I see this many faces in my talk, attending, my talk about lensing. So it's going to be fun, and I hope you will enjoy it. Uh, Thank you very much again for very nice introduction. So as uh, as you were told, I work in gravitational lensing, and today I'm going to talk about one part of my research, something known as lensing of individual stars. Okay, so individual stars, I don't have to explain that part, but today I have three jobs. First, to give you some basic idea about gravitational lensing. Second, to convince you that gravitational lensing is fantastic. Third, with to show you that with lensing, we are able to detect individual stars, light from individual stars, all the way up to half, beyond halfway across the universe. Even in the first billion years. So our universe is roughly like 13.4 giga years old, and time is basically like a distance measure for us. So if when we say that universe was this much old, so it's basically we're talking about past, at a certain distance from us. So but by the end of talk, you will see that what I'm going to lensing is just fantastic, and lensing is the only way to do what I'm going to talk about. Yeah. Okay. Okay. So here I'm showing you a galaxy cluster. Yeah. So where is the pointer? Are you able to see the pointer? Sorry, it's way too thin. Anyways, so you see my cursor. So all of these yellow galaxies are part of a galaxy cluster, cluster of galaxies. Many galaxies come together and form a galaxy cluster. And so today we will focus on these kind of objects, and how they do lensing. But first, let's have a little bit of introduction. So if you ask a very simple question, let's take our sun. So from our sun, we are observing certain amount of light. Now let's put our sun twice the distance that it is at right now. So right now it is 1 AU. Let's put it at 2 AU. AU is astronomical unit. So you can use the simple formula, and you will see that the amount of light we are going to receive, or the amount of flux we are going to receive, will be 1/4, because that is a typical formula that we use. This is how the the amount of flux decreases as we move any objects far away from us. So in astro, we have a very weird unit known as magnitude to measure how bright an object is in the sky, and we call it apparent magnitude. So it is defined something like this. It's a logarithmic unit. I'm saying it's weird, but it has a meaning behind it. So if you look at this equation, you will see that objects with negative values are brighter in the sky. Okay, the larger or the more negative the value is, the brighter it is on the sky. So what is the brightest object? It is our sun. So which has a value of -26. Okay, and moon is around like somewhere between -10 and -15. Now, with our eye in the night, we can see objects up to 6th magnitude. So as I'm going towards more, larger positive values, the objects are getting fainter. Okay, so you see stars. The faintest star we can see will be around like 6th magnitude. So that's how we say it. And the best telescopes that we have right now, they can go up. They can detect objects age as faint as 29th magnitude. And these best telescopes are Hubble Space Telescope and James Webb Space Telescopes. So these are the two telescopes that I'm going to talk about, or whatever I'm going to show is coming from these two telescopes. So now let's see how far we see with these two telescopes. So let's say we are sitting on the y-axis, okay? And on the x-axis, it's the distance from us. So the size of Milky Way is somewhere around like 10 to the 5 light years. So I'm assuming that you are familiar with basic light years, parsecs, and all these things. Please let me know if you are not, then we will introduce that also. So just with our eyes, we can see, so this is the farthest star that we can see with our naked eye. This is V762 Cassiopeia. And if you look at the distance, it's basically zero, in terms of cosmological sense. It's very close to us. It is around like a 1500 or 15,000, I don't remember, but this is light years from us. Now, so it is well within Milky Way, the size of the Milky Way. LMC, SMC, you might have heard about these things, large imaginary cloud, small imaginary cloud. These are somewhere around like less than 1 megaparsec easily, as you can see from the scale. Now, that is the Andromeda galaxy. Now, the farthest star that we can detect with our best telescope right now, individual star that we can see, is this one. It is a P42 in this particular galaxy. So this is how the galaxy look like with JWST. So if you take an image of this galaxy with our best telescope, this is how it's going to look like. And so these are the two images, taken of this particular star with Hubble Space Telescope and James Webb Telescope. So this is how it looks like. So now you're not resolving the star, like we see our sun properly resolved. You're basically going to see these things as point sources. So these are basically points in the sky. And they will be, how big these going to be, it's going to be determined by something called point spread function. We will not go into the details of those things. Now with lensing, we are observing light from individual stars, 1 to 2 order of magnitude far away, as you can see in the redshift and in the distance. So if you put everything in the context with our telescopes, we can go up to this point. And with lensing, we are observing stars, individual star, light from individual stars at redshift 1 and all the way up to redshift 6. So that's what we are able to do it just because of lensing. If we didn't have lensing, there were no other way to do the same thing. Now, what is lensing? That's the first question. So lensing is, in other words, it's bending of light. So let us say in this image, we are here on Earth. There's a faraway galaxy. And between that faraway galaxy and us, there is some mass distribution. It could be a single galaxy. It could be a cluster of galaxies. And today we are specifically focusing on clusters of galaxies. So what will happen is that this background galaxy is going to emit light in every direction. Okay, in each and every direction. Now, it is also going to emit light towards us. And what will happen is that some of the light rays, which were going, let's say, in this direction, as they pass close to this mass distribution, they will bend. Okay? And after this bending, they will come to us. And sometimes what can happen is that light that was going into this direction, light that was going into this direction, both of them will bend and then come to us. So what we will see the same galaxy at multiple positions. Because according to us, the light is coming from this direction and this direction. Okay? So this is known as gravitational lensing. This bending is known as gravitational lensing. The moment we see multiple images of the same object is known as strong lensing, because the bending is strong enough to give you multiple images of the same thing. And how does it look like in real life? So these are some of the examples. So in these pictures, you can see that in, let's say, this one, here there is this yellow galaxy that is sitting here. Now in the background, there was a source which has been lensed, strongly lensed. And instead of one source, now we see 4 images of the same source. So these 4 dots are corresponding to the same source, but because of the bending or lensing, we see 4 images of the same source. So this is here, the lens is a single galaxy. So we call it galaxy lensing by a galaxy. Now here, there are multiple, like you can see G1, G2, G3, G4. So there are 4 galaxies which are doing the lensing at the same time, coming together and doing the lensing. And it gives you this arc-like feature. Okay? So, here I just wanted to show you that, lensing can give you all kind of image configurations. It doesn't have to be like 2 images on the 2 sides of the galaxy or a galaxy cluster. It can give you all these different kinds of weird, if you want to call them, image formations. Now, instead of a galaxy, if you have a whole galaxy cluster doing the lensing, now in galaxy, typically what we'll have is a single source sitting behind the galaxy. But in cluster, because cluster is big, now you'll have many, many sources behind the cluster. So in one go, the cluster is going to lens many sources at the same time. So we will see multiple images of many sources. So for example, like here, I'm showing you one arc. So this is Able 370. This is the first galaxy cluster where we saw strong lensing in 1985. And this is one of the, well-studied cluster, and the one that gives us, nightmare, because it's very hard to model in certain ways. So for example, like this thing, it is a background galaxy at 0.73, and it has been strongly lensed, giving us this arc. Now, there is this galaxy, which has been, again, stretched because of lensing. And you can find other examples in this picture. So this is what strong lensing is. Now the question is, this is, pictures. How do we study this thing? So we come back again to this picture. Let's take this as our reference image. Now we are going to make some approximations. The first approximation we are going to make, there are 2 approximations actually. Something called thin lens approximation and small angle approximation. The thin lens approximation basically tells you that, the distance between us and the lens, between the lens and the source, between us and the source, they are huge. They are, like billions of light years. Now, these objects, this lens, so when I say lens, it's basically the thing that is bending the light. And the source is basically which is emitting the light. So both these lenses as well as sources will also have some line of sight extent. We are looking into this direction. There is a lens. It will also have this line of sight extent. Okay? But because this line of sight extent is very small compared to the distances from us to the lens, we say instead of treating it as a 3D object, we are going to treat it as a 2D object. We are going to project the mass in a 2D plane. And that's what basically what we did in this picture. So instead of 3D objects, we are going to squeeze them into 2D objects. So this is known as thin lens approximation. And the lens is now, we replace it with something called lens plane or image plane. And the source is source plane. This. The second approximation is small angle approximation. So far I've shown you, you can clearly see these deflections, light going like this. But that is exaggerated. In real life, the deflection or the bending is of the order of arc seconds in real cases. So for example, if you have a galaxy which is doing strong lensing, the total bending, how much light has been bent throughout the trajectory, throughout the path, it's of the order of an arc second. So it's very small. And that is why we say that we assume that all of the deflection is taking place in the lens plane or the image plane. So instead of having these smooth continuous bending, we say these are actually like this. So all the bending is taking place in the lens plane. So this was the 2 approximation, and after the 2 approximation, this is what we get. Now let's have some equations, and I promise these are the only 3 equations that I'm going to introduce in the whole this talk. Okay, so here I have also added some distances and everything. So DD, DDS, and DS, these are basically distances between us and the lens and the source, and us and the source. Now, there are some angles that we are going to need. The first is something called beta. If there was no lensing, then what would be the angle at which we will observe the source? You have a random reference. Okay, so theta is where we will observe the lens after lensing. Okay, so there are 2 angles. There's one more angle that we will need, and that is the deflection angle alpha, how much light has been bent. Okay, so these are the 3 angles. Now these 3 angles are related to each other by something called lens equation. So lens equation basically tells you that given a mass distribution, okay, you have the lens, so the lens will have certain mass distribution. So given the mass distribution, we can calculate the alpha, which depends on the mass distribution, bending angle. We can find if we have a point on the lens plane where it's going to go in the source plane. This is how it is related. Now, so for example, like you can take these rays. So there is this point on the lens plane, and for this particular lens mass distribution, it will go here. Okay. So for example, like here, I'm trying to show you like these three rays, black, are corresponding to the same source. So you will see three images. Now, the other equation we are going to need is something called Jacobian. So it tells you, like I've showed you that these arc-like features and all these things. But in real life, the galaxies, without lensing, they are just, more or less circles or something like that, much more simple. So this Jacobian tells you how the area elements are distorted as you go from source to the image. In the absence, let's say you had a circle in absence of lensing, but after lensing, you might not have a circle, you might have an ellipse or a much more complicated structure. So that is determined by this Jacobian. It again depends on the mass distribution. And the final thing we will need is something called magnification. So magnification is defined as, how much more or how less flux you are receiving compared to non-lensing scenario. So for example, like if you are receiving 5 photons per unit time, given a particular telescope from a particular object, then after lensing, what is the number of photons that you're observing? Okay, so it's basically the ratio after lensing and without lensing. So let's say if you're observing 15 photons, so then the mu will be 3, 15 divided by 5. So your source is magnified by a factor of 3 because you're receiving 3 times more flux now. So that's how the magnification is defined. Now, magnification, is given something like that, kappa, gamma. Okay, so the kappa and gamma both again depends on your lens mass distribution. And now you can see that for certain values of kappa and gamma, you can make the denominator 0. You can always choose something like kappa equal to 0.5, gamma equal to 0.5. That will give you denominator equal to 0. And then magnification goes to infinite. That is never going to happen. So this is happening because of our simplified treatment of the whole situation. But it tells us that there are regions in the lens plane where we can have high magnification factors. That's all. It does tell us that. So if we plot mu value in the lens plane, given a certain lens mass distribution, this is what you will see. So green regions are low magnification regions, or magnification roughly 1. The whitish regions are region where if you observe an image there, it will be highly magnified. Okay. Now you have two things. You have some quantity in the lens plane. You can use the lens equation to find the corresponding distribution in the source plane, because that basically relates the image lens or source plane. Okay, and in the source plane, this is how it looks for this particular lens mass distribution. Okay, so it's the same image again. Now what we can say is that any source that is sitting in the white region in the left side panel, which is the source plane, is going to be more magnified compared to the greenish source sitting in the green region. And so in the bottom row, I'm showing you one example. Like if you have a spiral galaxy, how it's going to look like if it is sitting. So you see that the green and the red line basically follows the high magnification regions in the upper panels. So if a galaxy is sitting on the red line, this is the kind of image formation that you will receive. Okay, so we can see that this image, and specifically this region, will be more magnified because this region we observe in the high magnification region. Okay, now from here you may have already got the idea that individual stars, we cannot detect them because they are too faint. Okay, without lensing they are too faint. So this might be the way to detect them. If a star is sitting into these white regions, like for example, a star is sitting here because the galaxy will have stars. Okay, so this way, this might be the way that we are detecting individual stars. But before that, the question is how much magnification these distant stars require. Yeah, please. Sure. So you're saying like if we have a source at 10 megaparsecs? Yeah, okay. So first of all, we are always talking about gigaparsecs. We are never in the megaparsec. Megaparsec is, close by. So the distances involved, like the DD, DDS, everything is gigaparsecs. Okay. Now, as I said, so you're talking about theta. So let's go back into this picture. Okay. So this whole thing would be roughly 3 to 4 arc seconds. Okay. So that's why I said like the galaxies will introduce deflection at most around an arc second. So this is the scale on which it's happening.
In this case,
With respect to us?
yeah, for this particular example.
Okay, so I do not know the exact values, but I can tell you the redshifts. Okay. And from there, if we look at this picture, redshift to the distance, we can go from here, but I know that, for example, in this case, this cluster lens is at redshift around 0.35, whereas this galaxy is at redshift 0.73.
0.35,
Seven, yeah.
For that background thing which is getting lensed, right?
Yeah, so this thing is at 0.73. This arc, it's a galaxy at 0.73, and after lensing, it has been distorted, and we are seeing this arc-like feature. And I will show you some more examples where the background galaxies are as far as like redshift 6, redshift 7. Okay. Okay. So now we got some idea that how we may be detecting these stars. Now the question is, how much magnification do these stars need, or how much magnification do they require for us to observe them with our best telescopes that we have right now? So that's the question. So these are some numbers that we did in 2022. So let me just zoom in on one particular, one particular set. So you see, for main sequence, so I showed you in earlier slides that our best telescopes can go up to like 2930. So let's take 29 as an example. So for 29, a sun-like star, which is denoted by main sequence, will require a magnification of 10 to the power 8. Lensing should magnify it, or should introduce so much. The lensing has to be so much that we are receiving 10 to the power 8 times more photons from that source. Lensing is not going to do that. Lensing is going to give you a high magnification, but not that much. There are limitations to lensing also. However, if you look at for example, like the Rigel, blue supergiant, Aldebaran, red supergiant. So these are nearby stars, which are, supergiants, which intrinsically, for example, like 100,000 times brighter than our sun. Okay. So they are intrinsically 100,000 times brighter. So the magnification that we will need will be like only of the order of 1,000 or 1,500, something like that. For example, like the Rigel one. And that much lensing can give you. That much lensing can magnify these individual stars at redshift 1, redshift 2. Okay. So from here, what you got is that lensing can magnify things, but it cannot magnify them, too much. And there is a limit to lensing also. But with lensing, we can detect stars which are intrinsically bright. Okay. We cannot detect all type of stars with lensing at those redshifts. Yeah. So this is, why this slide is here. Now, how do we actually, what is happening while we are detecting these stars, or while these stars are being detected? So let's go back to this cartoon picture that I showed you earlier. So in this spiral galaxy, there are stars. So think of it this way, that we are here. This thing is not working. Yeah, because I want to use my hands to explain. Yeah. Okay. So what is happening is that we are here, there is a lens here, and there is a source in the background. So all of these things are moving relative to each other. Okay. So there is this, transverse motion with respect to us between the lens and the source. Okay. So this galaxy is basically traversing through the caustic. So in that galaxy, there are stars. So they will get magnified and then they will, move away from the caustic. So in that sense, we can say these are transient events. You will see them today, tomorrow, or after a month, they will not be there. And this is the kind of light curve that you expect. So this is, initially when they are moving towards the caustic, they will, get more magnified. The moment they reach the caustic, they will reach a maximum magnification depending on their size. And mostly depending on their size. And after that, the magnification will go down and they will disappear. So this is a typical example. Now, one more thing that,
But if some black holes are there along the line of sight, then how to take into account their effect, like in your lensing?
So you're saying that black holes
Yeah.
in the lens,
Yeah.
in the lens?
No, somewhere in between, that can also bend the light.
Yeah,
no?
that's a good question. I will talk about that at the end of the talk because that's a completely different thing. Yeah, but please remind me. That's a fantastic question. Okay, so now we have seen lensing by smooth mass distribution, but in these clusters, what is happening is that you see this whitish hue. So that's the same cluster image, Abel 370. So you see galaxies, but around the galaxies you see this whitish hue. That is because of something called intra-cluster stars. So in galaxy clusters, stars are not just bound to galaxies. There will be stars outside those also. Okay, so the whole cluster is doing the lensing. Now these stars will also do the lensing because they also have mass. Okay, as long as something has mass, it will do lensing. So now this is what is going to happen to the lens plane. I hope you can see my cursor. So earlier it was like this smooth line, a single critical curve. And this is what it becomes after if you add stars also, which are doing the lensing. Now, if you take this back to the source plane using the lens equation, now you'll see something like this. Okay, so here earlier you just had one line. Now you have this whole network of lines. Okay, and every time the star crosses one of these lines, it will basically get magnified and then demagnified, magnified, then demagnified. So that is the kind of light curve that you would expect after that. And it depends like how much density or how much mass density is there in these stars. Okay, if you have too much mass density, they can actually remove all the bright peaks. That's what we see in the lower panel. You see that their height is not as much as the top panel as we increase the density. Okay, so this is what basically happens in a realistic scenario. Okay, so now I think we are ready. We know lensing can give you magnification. And if you're talking about clusters, in clusters, we also have intra-cluster stars, which will also do the lensing. They will introduce these multiple peaks. Okay. Now let us come to the detections. So the first detection of a single lens star at redshift 1.5 was presented, was published in 2018. So this is in Patrick Kelly et al. 2018 paper. So here they were actually not looking for stars. The first study was, way back in 1987, 1990, 1991. But people were like, oh, come on, you need too much magnification. It's not going to happen. So we are good anyways. So they were actually targeting a supernova. So a strongly lensed supernova was there. So this is MAX 1149. It's again a galaxy cluster. All the yellowish galaxies are part of the cluster, which are doing the lensing. And you see this thing. Yeah. So this is a spiral galaxy at redshift 1.49, okay, which has been lensed by this galaxy cluster. Now, you see these 4 dots. I hope you can see these 4 dots here. So these are the 4 images of a supernova, type 1a supernova, which is a rare thing and which is, very sought after. We need these kind of things, okay, to do something called, to measure something called Hubble constant. But I'll not go into the details. Yeah, so for this cluster, they had multiple images of the same thing at different years. Yeah.
Scattering of light actually change the magnification of the image when it reaches towards us.
Scattering because of like the gas or anything like across
yeah.
So that will depend on what wavelength you're looking at.
See,
Okay.
because it's coming from far away, and when the magnification comes, you already told there are 2 different images which are forming.
Mm-hmm.
So wouldn't it be more than 2 images? which would be forming?
So there could be like, okay, so 2 images, just an example. You can have 5, you can have 10. It depends on how complex your mass distribution is. Okay. If you need a more quantitative number, then if you have point lenses, let's say I just consider points, Gaussians, sorry, not delta functions, masses. If you have n delta function masses, they will give you 5 times n minus 5 images. So if you have 100, you have 500 minus 5. That is the maximum number of images that you can have. So it's not just 2, you can have many images. It depends on your mass profile as well as your mass profile, distribution.
So how do we know the accuracy of that particular image, that it's there? and not
Okay,
there?
that's a good question. So in lensing, there's something called odd image theorem. Okay, that tells, okay, let's go here. So in this image, so this is our source plane where we are going to move the source around. Let's say source comes from infinite into this direction. Okay, it is far away, lensing is more or less 0. It will have one image, because without lensing we will see one image. The moment it crosses this green line, 2 extra images are going to form, a pair of images. So we have 1, we have 3. The moment it crosses the red line, another pair of images is going to form. So 1, 3, 5, 7, 11. Usually this is how it goes. Okay, so most of the time you will have odd number of images, but sometimes, depending on the, again, mass profile, how steep it is, for example here, this central image might not even appear. Okay, so in those cases you will have even number of images. Okay, so this way we can, okay, so let's say if you look at this cluster and if you just see 2 images, then just by symmetry you can also say that there has to be another image on the other side. It might be very faint, but you can still predict that, okay, it should be there. So we do that actually, and then we go back again and check whether there is a sub image or not. Yeah, so we do that. Yeah. Okay, so they were actually focusing on this supernovae, but so while doing the analysis, they saw that in 2011, so now we are focusing only on this region, and there's this blue dot here, which, can you see this one? Yeah, okay, good. So it was not there in 2011, and in 2016 there was something. So then they said, okay, now we have detected another transient. What the hell it is? That was the question. Then they said, let's do the analysis. Okay, so our job is, we have detected a transient. Now to rule out different type of transients. That's our job, because we know that there is something. So this is HST. This whole thing is HST. This is a plot that I'm showing you. So they observe the same thing in different filters. Okay, HST will observe, in multiple filters like the red, blue, green, all these things. So these are basically the data points. These things. Okay. Now what you do is you fit spectral energy distribution, SED, to these things, and then you ask what fits the best. And then you see that it's star template. So star with temperature around like 10,000, 12,000 Kelvin fits the best. But then again, you can ask, is that the only way we can be sure that this is a lens star? Actually, there are more ways. I will tell you one more, is that blue supergiants have something called Balmer break. At 3646 angstrom in the rest frame, you will see a huge drop in the flux. That's what we see. You see in these, like here and here. I mean, we observe it at around like 10,000 angstrom because of the redshift. But in the rest frame, this is the rest frame wavelength, we see it exactly at 3646. So it basically, increases our confidence that this is a lens star. Now, other type of transient could be, like it could be a nova. It could be some, outburst in some within the cluster. But we have already ruled out that it has to be at the source. Otherwise, this break would not appear where it is. So this corresponds to redshift 1.48. Okay. Now, usually in lensing, there's something called counter images, which I basically talked about. So once you see one image, there has to be a counter image also somewhere. So if it was a nova or something like that, we would have observed one more image somewhere around here, but we don't see that at the same time. Okay, so that also rule out a lot of transients. So ultimately, Kelly and that all, they said that it has to be a lens star. There's nothing else that fits the overall scenario. Okay, so that was the first detection. Now this, yeah. Asymmetry in
in the light distribution, right? No.
so this is lensed. So
Yeah.
usually what lensing will do, it will create two images
Right.
like this one.
Right.
Okay?
Right.
So there will be two images on each side of this line.
Right.
Okay, and here we do see that. So there is this one and there is this one. Okay, that's why I took the example of spiral galaxy, because it's easy to convince, like, okay, that, you know, the first example was also spiral. So you see these two galaxies. Now in one of the arm, let me try to zoom in here. So this is basically how it looks. Okay, so in one of the arm, one of the star crossed a caustic and it went up.
Okay.
And that's why we were able to detect it. Yeah. Yep. Okay. Great. Okay. So now the question is what we can do with these stars. I mean, we are detecting these stars. That's fantastic. But what is it that we can do that we were not able to do earlier? That's the question. Now, first obvious answer is that now you can study individual stars at redshift 1 and beyond. You know, that itself tells you something, because the constituents of the universe were different. The metallicity and everything was different. Universe was much younger. Okay, so that's one thing. You can study these individual stars. And so, for example, like we detected two stars. Now I'm going. So this was one application. So now I'm going to talk a little bit about detections. So we detected a pair of stars at redshift 4.8. So this is the cluster, max 0647. The cluster itself around like 0.55, or sorry, 0.6. And we detected the star at redshift 0.79, which is 0.8, 4.8. So in this one, so this is the arc. In this image, it's here. Okay, so all these yellowish galaxies are doing the lensing. Don't focus on these greenish things. These are, you know, the data reduction was not working well, and these are some of the artifacts you face during data reduction. So this was the arc. It's at redshift 4.8. And when we looked at it closely, you will see that, you know, if you start from the top, there is this thing, there is corresponding this thing. I said that things appear in pair. So if you keep going down, then you will see that for everything, there's a pair. But for these two things, there's nothing. The symmetry is broken. So this is a transient. Okay. Otherwise, there would have been something else on the other side of this yellow line. Okay, but we don't see anything. So, sorry?
Images.
Yeah, this is JWST. Yes. So now we again did the fitting and everything, and again, lens star, a star around like the temperature 10,000 fits very well. Okay. Then we said, okay, we are still not sure because we just had one epoch. We didn't have multiple epochs. You know, we didn't see it as a transient. We just saw it. Then we said, let's take spectra of this thing. You know, so again, JWST, there's something called NIRSpec that takes spectra of these things. We took this spectra, but it was not very encouraging, because in spectroscopy, there's something called R value. What is the resolution of your spectrum? So that was not great in our case, because the amount of time that we asked for, that was not enough. And we were not able to see lines or anything. So with this, we said that, you know, in principle, you can fit star, a binary system. Like binary is on the left, in the middle there is a star, and on the rightmost panel, if you try to fit a star cluster, a bunch of stars. But in case of star cluster, you cannot reconcile, you know, the size of this object that we see and what would have been, you know, it's a lensing corrected size, because lensing magnifies things. It makes them bigger. So if you go back and you find the exact size of this thing, that would have been too small for a star cluster. So we are saying that, you know, it has to be a binary of a single star. We do not know. More observations will be needed for this. Okay. Now, after that, we said, you know, let's go to even higher redshifts. So that's what our thought. So we said, we have this cluster, and in this cluster, we have one arc. So there are two arcs, one at redshift 3 of 2.9. The other is redshift 6.7. So earlier was 4.8. 6.7 is even farther away, okay? So we said, let's target this thing. So by the way, this is JWST image. So we said, let's target this with JWST. Let's try to see if we find some stars. Unfortunately, we didn't find anything here, but it also revealed some interesting stuff that we put out in this paper. Okay, so that was the first application, studying individual stars, trying to figure out their properties, in faraway universe. The second is something called constraining the stellar IMF. IMF stands for initial mass function. When stars are born, we believe that they are born using certain mass function. Okay, and the best candidate that we have right now is something called saltpeter. Okay, and Krupa, Chabrier, these are different parameterization. Okay, so usually this goes something like this. So we can actually constrain the slope of this alpha value. We don't know whether this is universal, this initial mass function that we are assuming, whether it's the same as our galaxy, whether it's the same everywhere in every galaxy, we have no idea. We do have some idea, but we are not sure. So we said, let's do it at redshift 6. Let's do it at redshift 1. So that's the second thing that you can do. So here we did this work. So here we took a sample of like 17 arcs. And then we said, in out of these 17, you detected n number of events in m number of arcs. So you can, reverse engineer it. Okay, what kind of IMF will give you this number of events? So we basically took two alpha values. 2.35 corresponds to saltpeter, which is a very well-known initial mass function that we have. And the other is alpha equal to 1. Alpha equal to 1 will produce more bright stars in the universe. And as expected, that predicts too many events. Okay, so yeah, so our value lies somewhere in between, but we also did some follow-up analysis. And so far, it agrees with saltpeter. But again, large error bars so far, because we need a larger sample of these events. Okay, so the third application, that is constraining the nature of dark matter. Now, remember, initially I said that the moment you put these intraclustered stars, there will be more peaks. And if you put too many stars, the peak height will go down. Okay, the peak magnification will drop. Now, we know that clusters have dark matter. Okay, usually we assume that it's in the smooth form. Let's say we take 1% of the dark matter and we replace it with compact. We replace the smooth form with compact form. Okay, so now they will also behave as lenses. Okay, and they will also give you something. They will also give you peak, or they are going to destroy some peaks, or they will do something ultimately. And they will affect the number of these lens stars that you would expect in a given arc. So that is the overall idea. Now, this figure is taken from Venumadhavan 2017 paper. So this was before, so this is more of a forecast. So I just want you to focus on this one. It says that, with the lens stars, you can constrain compact dark matter up to 1%. If more than 1% dark matter is in form of compact, objects, you can constrain it, or you can tell whether that is the case or not using these lens stars, detection of lens stars. Now, in 2018, Masamune Oguri, so he asked a simple question. We have detected one event, the first event. Just based on that, what can you say about the compact dark matter or its fraction? Simple question. So if you add too much dark matter, what it will do, it will basically smooth out these peaks. So even if you have very bright stars, we will not be able to observe them. Okay, so you cannot put all the dark matter in compact objects. You can only put a certain amount so that we still detect that event. So that's basically Masamune did. And he said that if you put more than 10% of the dark matter in compact form, you will not be able to observe lens stars. So that basically puts an upper threshold. Okay, so the compact dark matter has to be less than 10%. Okay, now in Muller and Miralda-Skewed, they did this analysis in 2025, last year. So instead of taking one event, by this time we had like more than 100 events, like 200 events. So they said that we are going to focus on 9 events. So they took 9 events and they again did the same analysis. So then they said that we detect these 9 events, we can put some constraint on the nature of fraction of compact dark matter, and they said that it cannot be more than 2% in above 10 to the minus 6 solar mass. Okay. Now, so this is compact dark matter. Now, what about other form of dark matter? Because we do not know what dark matter is. So there are different models of dark matter. Okay, so Yoshinobu Fudamoto in 2025 detected 46 events. So why I'm showing you same image of this dragon arc again and again? Because this is one arc. Whenever you look at it, it will give you caustic lens stars. So I'm saying caustic crossing events because that's the other name of these things. So if you look at it today, you will see some lens stars. You look at it after a week, you will see some lens stars. So because it's close by redshift 0.73, and it is so bright, the magnification is just too high here. So every time we look at it, there are some events. So it's a fantastic place to actually observe more and more events to build your sample of lens events. So Fudamoto detected 46 events in this arc, and it was published in 2025. Actually, detection was in two epochs, which were taken in 2022, 2023, but it took some time to get it published. Now, Tom Broadhurst, he said, we are detecting a certain distribution of these events across the arc. So in the bottom panel, I'm showing you the same arc zoomed in version, and all the dots are locations where we have detected lens stars. And the white line is basically the infinite magnification line. Okay, so you see that most of the time we only detect around that as expected. So he asked the question. So usually we assume that all the dark matter is non-relativistic. Okay, so that's something called cold dark matter. Although we don't know its nature, but we do have some upper limits on its velocity and its interaction and all these things. So that's a vanilla model, vanilla LCD model. So he said, I'm going to replace the cold dark matter with something called fuzzy dark matter. You don't have to know. It's just the idea that I want to convey is that if you replace the best model of dark matter that we have with something else, then it will give you a different type of distribution of these lens stars, and which is basically like is shown in here in these two panels. I'm not sure whether you are able to see these numbers, but the idea is that the moment you change the nature of dark matter, the locations and how far you can see these events, that is going to change. Okay, for example, like if you have fuzzy dark matter, you will see events slightly far away from your this white line. And why is that? Because this particular dark matter creates these pockets of high magnification even far away from here. Some of you might be thinking, okay, I'm not able to understand, but that's not the point. Point is that with lens stars you can actually differentiate between different dark matter models. Okay, so these are the three applications on which we have basically worked on so far. And so I can tell you that in 2026 alone, in this arc, we have detected, I think, 104 events. Okay, it's basically, there was this program that we put out. We asked JWST to observe this arc, at a regular interval. And in addition to these 46, in addition to earlier, like, I think 10 events, now we have detected 104 more events, and many more are on the way because we have more data on this particular system. Okay, so these are the three events that we are working on, and so I think that was a lot about these lens stars. So finally, let me just advertise a little bit. So we are working on this lens factory lens modeling software package. So right now, if you want to learn basic lensing, please feel free to check it out. And if you find something complicated, let me know. Just drop me an email and we'll figure this out. And so right now we can do mass modeling also. And soon we will have support for these light curve that I showed you. So we already have the whole code. We're just going to implement it now. Okay, so now I will just summarize my talk. So hopefully I have convinced you that lensing is fantastic. Lensing is the only way we can detect individual stars or study individual stars very far away in the universe. And I showed you, I explained it to you that why it is happening. It's because like lensing can magnify background objects, and how much magnification there is going to be, it depends on the size of the object. And I showed you 3 applications of this with some pretty nice pictures. And these are my collaborators. So this work was done during my postdoc and up to very recently. Yeah, with that, thank you very much for listening. Yes. So just a second. So now you asked a question. So I remember. Okay. So you are saying that if you have cluster and then there is some black hole or something, so that basically constitutes part of the dark matter. That will come into the picture as dark matter. Okay. So we can constrain lensing by it also. But a single dark matter, we will not be able to say much. But if there is a population of dark matter in form of black holes, like primordial black holes or something, then we will be able to constrain that fraction also with these events. Because lensing doesn't care whether it's a black hole, compact, some other type of object. Lensing is mass sensitive. So we will be able to, yeah. But we will not be able to tell different, whether it's a black hole or it's something else. Yeah.
Yeah, so if I understood correctly, so you were talking about that stars which got lensed and all, which belonged ideally to a galaxy,
Yes.
which got, let's say, lensed. And so at what distance we are talking about? Redshift, you said 0.6 or so?
Okay, so let's go here. Yeah. So this tells you distance of, so on the upper x-axis, it's the luminosity distance of these objects.
Right,
So without lensing, we can go up to this point.
right.
With lensing, so this is the red arc that I showed you. It's
Right.
the closest one.
Right.
Which is somewhere around like, 20 giga, 20 billion light years or something like that.
Okay. So what is this medium which is lensing it? This particular, what is it you are
It's
considering?
the galaxy cluster.
Cluster. Okay. So you have cluster, and because why this question is coming to me is you are mentioning like that could be a star, and you looked at the spectrum and all, right? No, but don't you think at that particular distance, when you look at that size, that shouldn't be a star, but rather a group of stars? I mean.
Okay, so there's one important distinction here. So we are not able to resolve the star.
Correct.
We are just detecting them as transients.
Correct.
Okay, so
Yeah.
we will see excess of light.
Right.
We are not resolving them.
Correct.
So the resolution will be fixed
Yeah.
by our telescope,
That's right.
the diffraction limit.
Right.
So even if you replace the star with the star cluster, it will still, we will be able to see it as a point.
Correct.
That will be no more
Yeah,
than that.
but I was thinking more in terms of that similar argument. If you are considering that more like a group of stars in that sense, that will be much more interesting, right? No, in the sense, and were you looking into the IMF saltpeter distribution for that particular source, or the whole stretch which got lensed?
Yeah, so it's basically like in the source, you will have, so if the stars were born with some profile, so the whole galaxy is getting lensed. So all of the stars will be lensed, okay? But only the high mass end of the IMF, we will be able to observe, because only these stars will be intrinsically bright enough for us to actually observe them with the lensing.
Yeah.
So that is why I specifically said like high mass end of the IMF.
Yeah.
Yeah.
Because I would have expected a different value than saltpeter if that was the case, right? No, because the way we address the IMF in the galaxy, where you have the whole population available, instead of that, in the context of lensed, it's skewed population.
Yes.
So which means IMF should be different from the classic number.
No, okay, so obviously the population that we are seeing, it is skewed. We are not seeing the low mass stars, but you have to correct the whole sample by the lens magnification, and while doing that, you also have to fit templates and everything. So you're basically, from observed sample, you go back to like what would have given rise to this population of observed events. So that's the question. That's how. So that, I don't think so that would matter.
Okay.
Because it's only the upper part of the, or the heavy mass end of the mass function that we are actually able to probe.
Another quick question.
Sure.
If you're considering the, let's say the as you said, the galaxy cluster or something which is lensing to be, let's say, X, what is the distance you are from there to the other object in terms of X? Can you tell me?
In
like,
terms of its x, it will be of the same order.
same order?
Yeah. Let's say so in this case, you can see that, so here I'm showing you luminosity distance, but usually we use something called angular diameter distance for these DLS, DS, and all these things. So at redshift 2 is around like 1700 GPC or something like that. And the lens would be sitting somewhere halfway across, because that basically maximizes our lensing probability.
Objects, right? So what if, sir, if instead of black hole there is a white hole, theoretical white hole,
Okay.
in place of that?
So I don't think so I can comment on that, because I do not know what a white hole is. But yeah, so as long as it has mass, lensing will be there. That much, yeah,
So
we
we
can be sure.
theoretized white holes as a as black holes like dip inside the space-time curvature. White holes will have anti-mass and will it will shoot upwards
So in that case,
yeah.
the sign will change. So you're basically changing the sign of the mass.
Yes.
So lensing depends on something called, lensing is proportional to the mass. The more mass you have, the more lensing you'll have. But you are basically removing the mass from there.
Yeah, it is working on anti-mass.
So think of it this way. Like it will go in the other way.
Okay.
But I'm not saying that this is the way, because I do not know about white holes. It's my limitation to answer that question, not you.
Okay, sir. No problem.
Yeah. Multiple galaxy clusters. Okay, so what you can do, so let's say we are here, you form a beam, a cone-like shape, okay? You go all the way up to redshift 1, 10 arc second, something like that, or 20, 30, or 1 arc minute. Then you calculate what is the probability of having more than one galaxy clusters in this line, in this beam. If it is, probability of having more than one, if it is very less, then more or less you will end up with one galaxy cluster in this line of sight. So you can calculate that, and you will see that it turns out that it's most of the time it's less than one. Okay, so most of the time you will have just one lens. However, I should mention this, like one of the example that I showed you, this one. So in this one, the whitish galaxies are the galaxy cluster, and behind it at redshift 3 there is a galaxy group which has been lensed. So now that galaxy group can lens something else. So these kind of scenarios are there, but the probability is low. Okay.
May I now request our faculty coordinator, Dr. Aditya Singh Mehra, to kindly come forward and present a token of appreciation. On behalf of the Department of Physics, I extend our sincere gratitude to Dr. Ashish Kumar Meena for delivering such an insightful lecture under our flagship initiative, Raman Lecture Series, and for sharing his valuable knowledge with us. I also thank our respected faculty members and dear students for your enthusiastic participation, which made the session a success. With that, we conclude the first talk of the Raman Lecture Series. Thank you all for being here. Have a wonderful day. Thank you.